So this is a scheme, a finite difference scheme for the second derivative. In a different video, we proved the value of the coefficients. What we're going to do is we're just going to check what the order of these of this approximation. So it's obviously important to know the accuracy of our scheme, and the truncation error gives us an indication of what that accuracy is. At least it's like the biggest thing that we've neglected. So recall that we did this by Taylor series. We wrote down a Taylor series for f of x at naught, at x naught here. So let's just do that again. So f naught plus x minus x naught, first derivative at naught, 1/2 x minus x naught squared. Right, and this is where we stopped. We neglected things of third order, that looks like this, right? We just said, okay, that's the higher order term. Okay, so let's just write this out now and see what happens to our higher order term when we plug in this approximation up here into our finite difference scheme. So we'll write out what f1 is. X naught plus h, right? We move to x naught plus h minus x naught. That just gives us an h. Oops. This will give us an h squared thingy. This will give us something order h cubed. Okay. F2 is very much the same. Now, that factor of 2 out the front, or a factor of 8 or whatever it happens to be, that's still going to be dominated by the h cubed. So we still say that this is order h cubed, even though this thing is 8 times that one. Right, we're assuming that h is pretty small. Okay, so plug this in up here. One on h squared f naught. That's our contribution there. Our contribution here is minus 2 h squared f naught. H cubed like that. And our final one, I'm just going to write it down here to save some room. Sorry, it's 2h. Two h squared f double prime naught plus a whole. All right, so what we see is the following. This, and this all cancel out. Obviously that must happen. That's what we designed our method to do, right? We know that these coefficients were selected, that must happen. Similarly, this term, which is minus 2 on h, right? That's going to cancel with this one here. This term here, oops, I've forgotten the f double prime when I wrote it out. right? Again, we're going to see the h's cancel. We're going to get the 2's cancel. Hang on a sec. Where did my 2 go? Why did my 2 not cancel? It's here. I forgot to divide. Oh, I did divide that by 2. Hang on, I'm going to pause and find where my 2 went. Okay, I found it. It's this bit here, this bit here, has to equal that bit there. So what we'll see is we've actually got minus 2h squared times h squared on 2 f double prime plus, so that gives us a minus f double prime plus 2f double prime. That's equal to f double prime here, right? So everything in this equation balances with the exception of these terms here. These are our first unbalanced terms. So let's see what happens to them. What we've got is we've got an h cubed term divided by an h squared term. This is of order h, right? So that's actually a lot worse than what we expected. We neglected terms like h cubed, but when we actually plug into our method, we find that our truncation error, remember that this is the first stuff that we dropped, is actually of order h. This method is only first order. So you can kind of see a bit of a pattern. We use 3 points for a second derivative. So the error term is kind of like the number of points minus the derivative in this specific case, right? So for, say, forward difference methods like this, you can sort of be assured that if you've got 4 points on your right-hand side, you're going to get a second order method. If you've only got 3, you got a first order method. If you only use 2, well, that's a 0th order method. You've got a terrible approximation to your derivative that you're actually trying to approximate. So even though you might neglect h cubed, which you think is pretty small, because your coefficients end up looking like 1 over h squared, that approximation isn't actually too good. And if you want to improve it, you need to include the third, say fourth, a couple more points to get better methods.